Welcome to lesson 5.3, use angle bisectors of triangles. So the first thing we need to refresh ourselves on is the idea of an angle bisector. So let's look at the angle down here, angle BAC. So from B to the vertex of A to C. That large angle is being bisected by ray AD, meaning ray AD splits our big angle BAC into two equal smaller angles. So AD bisects angle BAC into angle BAD and angle CAD. Those two parts are equal. So an angle bisector is a line or a ray or a segment that cuts an angle into two equal parts. So making sense of that then, we have two theorems, 5.5 and 5.6. 5.5 is known as the angle bisector theorem, and it states if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. So in this case, if AD is bisecting angle BAC and DB, so DB, this segment, is perpendicular to side AB, and in this case, if segment DC is perpendicular to side AC, then we know the distance from B to D is equal to the distance from C to D. So D is equidistant from B and C. So any point along AD would be the same distance to each side. And then 5.6 is the converse of that. The converse of the angle bisector theorem states if a point is in the interior of an angle and its equidistance from the sides, then it is on the angle bisector. So if we were told point D to B is equivalent to D to C, so if DB equals DC, then ray AD is the bisector of angle BAC. So if we know the point is equidistant from the sides, then we can say that AD bisects BAC using the converse. If we know AD is the bisector, then we know D is the same distance from B as it is from C. Those are our two theorems. So example 1 is asking us to find the measure of angle GFJ. So find the measure of G to F to J, so this upper angle right here. So what do we know? Well, in the diagram, we know the distance from G to J is 7 and J to H is 7. So that tells me J must be on the bisector because it's the same distance from each side. So ray FJ bisects angle GFH. So that means if our angle down here, HFJ, is 42 degrees, that's equal to GFJ. So GFJ, the measure, must be 42 degrees also. Example 2. For what value of x does P lie on the bisector of angle A? So what value of x would mean point P would be on a bisector of angle BAC? So that means the distance PB must be equal to PC. So in other words, x plus 3 must equal 2x minus 1 for P to be on the bisector. So x plus 3 equals 2x minus 1. Then we can solve for x by subtracting x from each side. So 3 equals x minus 1, add the 1, and x would equal 4. So what value of x makes P on the bisector of angle A when x equals 4? And then example 3. Do we have enough information to conclude that ray QS bisects PQR? And in this case, no, we do not. Even though they tell us SP is equal or congruent to SR, what we also need to establish is that segment SR is perpendicular to QR and that segment SP is perpendicular to QP. If we don't know that 90 degree here and here, we don't know if these angles were at the same measure, so we don't know if it's truly equidistant. That's why you'll see here we have those right angles. Same with here, here, and here. So we need that perpendicular part of the theorems. Without it, we can't use either one of those theorems. Then we get into our third theorem for today. The third theorem, 5.7, is known as concurrency of angle bisectors of a triangle. And in our last lesson, we looked at concurrency of perpendicular bisectors, which met at a point called the circumcenter, in which we could draw a circle that the triangle fits inside of. Well, now, angle bisectors of a triangle, they also meet at a point. And in this case, the angle bisectors intersect at a point that is the same distance from all the sides. So point P would be the same distance to D, to E, and to F. So what we know here then would be PD equals PE, which equals PF, as long as segment AP, segment BP, and segment CP are all angle bisectors of the three corners or vertices of the triangle. And just like last lesson, I will put a second video showing you how to do the construction of your angle bisectors. And then the idea of this point of concurrency. In the last one, it was called the circumcenter. Now, if we're finding the point of concurrency of angle bisectors, it is known as the incenter. And the reason that we call it the incenter is that, number one, always is inside the triangle. And if we use a compass and set the point to our incenter, and then set the distance to one of our sides, we can fully inscribe a circle within the triangle, which would be right here. So the incenter allows us to draw a circle within the triangle, where our circumcenter allowed us to draw a circle outside of the triangle. So the idea of the incenter is it's equidistance from each of the sides. And then we get to our final example for today, example 3. Tells us in the diagram, N is the incenter of triangle ABC. Find the distance ND. So we're finding the distance from N to D. So what do we know? If N is the incenter, we know that the segment ND, NE, and NF are all equal. They're all the same length. So if we look at triangle NAF, so triangle N to A to F, this little triangle up here, we know that NA was 20, we know that FA was 16, so we could use the Pythagorean theorem to find NF. And we're going to come back to this idea more with the Pythagorean theorem, but I'm just going to show you the process here to get the ball rolling. So if N is the incenter, we knew that NF would be the same as ND and NE. So I'm going to try to find NF. Now, what the Pythagorean theorem says is that one of the legs squared plus the other legs squared always equal the hypotenuse squared. So the hypotenuse of triangle NAF is the side opposite the 90-degree, or side NA. So NA is on its own, or the hypotenuse. That would be 20 squared. So 20 squared would equal NF, which is x squared, plus AF, which is 16 squared. So then we have 400 equals x squared plus 256. Subtract the 256, and 144 equals x squared. So the square root of 144 would be x, which is 12. So in that case, if x is 12, NF, ND, and NE are all 12. So just giving that idea of, if we know N's the in-center, if we can find the length of one of those segments connecting it to a side, we know all three are the same. And again, we're going to come back to this idea of Pythagorean theorem, but we can use it to figure out side lengths of right triangles. But the main ideas for today go back to the point of concurrency being the in-center of our angle bisectors, and then our two angle bisector theorems.